Okay, so we look at the sum of these two expressions. And we do the arithmetic and we get this, and everybody knows how to do this, I think. Most of you are very good at doing this. Okay? Now I want to look at this in terms of our basic functions. This is just the 1 over x function, where x has been replaced by x plus 2, right? That means this is horizontally shifted 2 units, negative 2 units in the x direction from the 1 over x function, right? What about this one? Well, first of all, if you have the 1 over x function, you'd better multiply it by 3 to get 3 over x. You're going to need to multiply by 3. That's a vertical stretch by factor 3. Everything moves 3 times as far from the x-axis. That's what a vertical stretch does. Make sure you understand that. It'll be important for your test grade, okay? And very important for understanding these functions and how they work in the real world, which is the ultimate goal of this course. The main goal of this course. And that's so that you take a calculus course, an applied calculus, or an engineering calculus course later, you'll have the vocabulary to understand what's going on. Okay. And then you're going to horizontally shift it. You're going to replace the x by x minus 1, which means x has to be 1 unit bigger to give you the same y value, which shifts everything 1 unit in the horizontal direction, plus 1 unit to the right. So we summarize that here. So now we have these two functions. We know what the 1 over x graph looks like. Okay? And we're just going to shift that graph negative 2 units. And wherever negative 2 is, if this is 1, then this graph shifts over like so. So now the vertical asymptote is at x equals negative 2, and here's your new graph. Okay, then we do the same thing with the same basic function, but we vertically stretch it by factor 3, meaning every point moves 3 times as far from the x-axis, meaning that this point, which is this far from the x-axis, has to move, and we move straight away or straight toward the x-axis or at a perpendicular with the x-axis. This point moves up here. Remember doing this? Now's the time to lock in why we did that, okay? If you didn't lock it in originally, many of you did, but as I say, this is a topic where people have a little trouble. This is what a vertical stretch does. And what people are doing with a vertical stretch is they just move everything up 3 units. It's not a vertical stretch. It's a vertical shift. Okay, so now your graph is like this. Okay, and you do the same thing down here. I'm just going to shift this part because we know the other part's going to look very similar. And then we shift it 1 unit to the left, so that now our vertical asymptote is at negative 1. I'm sorry, we shifted 1 unit to the right. Not paying any attention. So our vertical asymptote is at x equals 1. So if this is x equals 1, every point moves this far to the right, giving us a graph like this. It's going to have a vertical asymptote at x equals 1. And on the negative side, you're also going to have the same thing. This is going to stretch and then shift, and you'll end up with something that looks just like a kind of an inverted mirror image of this. Okay? Make sense? Yeah, it's something you should ideally know by now because we've done a fair amount of it, but it's apparently something that's hard to grasp onto, so keep working at it. Got 5 days. Okay. So now this function has to somehow be the sum of this and this, right? Now, if we continue these graphs both, when x gets big, the denominator gets big and we get a small fraction, so the number approaches 0, right? In other words, y approaches 0 when x gets big here, right? If we get away from where it's, the vertical asymptote, it's going to approach the x-axis. So this function gets small and kind of stays small. What do I get if I add these two functions? Well, without going into a lot of detail, although we've kind of depicted this, I think, we haven't done a lot with it. This function has a very small y value. This function has a great big one, right? So when we add them, this is going to be dominant over this, because this isn't going to add much to this. So the graph's only going to be just a little bit higher than this one. And similarly, over here, it's only going to, this function here is very small. This one is very big, so the graph is going to be a little above this one, but not much. Now, when this one gets big in the negative direction, this one's small, so the graph is going to do this here, and then over here, let's not worry too much about it, but the graph is going to pretty much be close to this one, because this one's going to be very close to 0. So we'll just kind of do that. Okay? Now, in between, it's got to do something else, and in between, these things are kind of arguing with each other. But at about this point right here, this one is as high above the axis as this one is below the axis, which means the value of this function, the y value is some positive number, and the y value of this one is equal and opposite to that. It's a negative number with the same magnitude. So these two on this line are going to add up to 0. So what happens is this comes down here, but at some point it's got to do this kind of thing and it goes down here. It really doesn't quite level off, but it has something, behavior that looks like this. Over here, this one stays small, so this one just kind of almost merges with this one, and this one kind of merges with this one, and there's the graph of our total function. Does that make any sense at all? Well, I want you to have the picture now and relate it to the fact that if you add these, you get this. And if you add this graph to this graph, it's going to look like this. Okay? Then we can say this. Common sense. What does x have to be to make this one 0? Give you a hint. If the denominator is 0, what do you know about the value of this function?
0. It's undefined.
It's undefined. Okay? Denominator 0 means you're dividing by 0. So unless the numerator happens to be 0 for the same value where the denominator is 0, it's undefined if the denominator is 0, right?
So 1.25.
Huh?
So 1.25.
Are you talking about 5/4? Yes, you are. Okay, yeah. But something wrong with what you said. Okay. Well, if the numerator is 0, what's the value of this fraction?
0.
Yeah, if you divide 0 by a number that isn't 0, what do you get? How many times does a number that isn't 0 go into 0?
All of them.
No times. Okay? We've talked about this. Okay? And this is something you should have learned very well when you were 7 or 8 years old, or maybe 9 when you learned a little bit about division, or maybe 10. Okay? Unfortunately, somebody put a calculator in your hand and you never have to think about it again. Okay, but you understood it at one point. You need to understand it now, and I've told you this before, so you need to make a note of this. If you don't understand these things, you are not going to understand what's coming up with rational functions. If you divide 0 by something that isn't 0, you get 0. But if you try to divide a number that isn't 0 by a number that is 0, you can't define it. I spent a lot of time one day talking about that. Got to know that. Okay. So anyhow, if the numerator is 0, that makes the whole thing 0. Well, you set 4x plus 5 equal to 0 and solve the equation, which I know you can do. You're going to get x equals negative 5/4. I don't think you said negative. It's still good. Okay? Well, does it make sense that the way this graph was drawn, that this would be at about x equals negative 5/4? Well, here's your y-axis. It's to the left of the y-axis, right? That wasn't very accurately drawn. They actually, I think on this scale that'd be even a little less than 1, or to the left. But it's in the right approximate place, isn't it? So by reasoning out in terms of the horizontal and vertical shifts and what these two functions do and what happens when you graph those two functions, then think about what happens when you add them, you get something that makes perfectly good sense. Maybe it's not totally accurate. That depends on your ability to draw these things accurately. But it's in the right place. Got to be between here and here, and probably closer to the left of the y-axis. Okay? Also now, for what values of x is the denominator 0?
1 or negative 2.
Again, I'm sorry?
1 or negative 2.
Yeah, if x is 1, this is going to be 0. That's going to make the whole denominator 0, right? And if x is negative 2, this is going to be 0, which makes the whole denominator 0. And that should be completely obvious to you. Okay? Again, if not, you need to do a lot of reviewing. Now, if the denominator is 0, what happens if x is real close to 1, but not quite negative, but not quite 1? Then your denominator is going to, how would you describe the value of your denominator? Well, first of all, if x is really close to 1, what can you say about x minus 1? I think you can say it's really close to 0, right? And if x minus 1 is really close to 0, what do you get when you multiply that by x plus 2? Well, it's still close to 0, right? And if you're really, really close to 1, the denominator is still going to be really close to 0. And the numerator isn't going to be close to 0. Okay? Now, if the denominator is really close to 0 and the numerator is not really close to 0, what can you say about the division, the result of the division? You divide a really tiny number into a number that isn't tiny. What do you get?
Bigger number.
You get a big number. Because a tiny number goes into a big number a lot of times. Or a tiny number goes into a number that isn't tiny lots of times. Okay? So this gets big. Well, here's x equals 1. What happens to the value of this function? It gets big. It gets big on this side, but it's a negative big, but that's okay. Right? X might be a little more than negative 1, or it might be a little less than 1. So one way it'll be positive, the other way it'll be negative. But either way, you're going to get a lot of, it's going to go into the numerator a lot of times, even if it's a negative a lot of times. That's just intuitive. Similarly, when x gets close to negative 2, this gets tiny, this doesn't, so the division gets big, and that's what happens near negative 2.